Consider a long resistance wire of radius of 0.2 centimeters and a thermal conductivity of 15, in which heat is generated uniformly as a result of resistance heating at a constant rate of 50 watts per centimeters cube. As shown in the figure, the wire is embedded by a 0.5 thick layer of ceramic whose thermal conductivity is 1.2. If the outer surface of the temperature of the ceramic layer is measured to be 45 Celsius, determine the temperature at the center of the resistance wire and the interface of the wire and the ceramic layer under steady conditions. Okay, so what is happening here? There is this fella here, and we know its temperature right there, right on this place here, is 45 Celsius. If we look to this guy in this direction here, if we're looking in this direction here, we would see something like this, right? In which inside we would have a copper wire, and then outside we would have this ceramic layer. Cool. Now, what is happening here? We're seeing energy being generated. What does that mean? Well, this copper wire probably, and this EGen is the first time you guys see this. This copper wire is probably electric current going through this copper wire, and then we know that due to the Joule effect of the atoms hitting each other and hitting against things, creates heat, right? So this copper wire is heating up as electricity is going through it. And it's heating up, it's giving away energy in the form of 50 watts, not in the form, but in the amount of 50 watts for every centimeter cubed of copper that we have. Okay, now, one sentence that's very, very important to be able to solve this problem that we were going to do is this last one here, okay? Under steady conditions. What does that mean? What does that mean? It means that enough time has elapsed for this to be under steady conditions. So this means that the 45 Celsius that we read over here, will not change no matter how much time elapses. It can maybe 1 minute later, maybe an hour later, infinity later, this will still be at 45 Celsius. Because whatever energy that we have coming from this copper wire in the center here, whatever energy that is coming from the center here is eventually leaving the system, right? So we have a constant Q going in this direction. If Q were going in this direction, then this copper wire would increase in temperature over time, right? That's the only possibility for it to be steady state condition is for the Q to be leaving, so that we create a temperature gradient in which we have the greatest temperature right in the middle, and the temperature decreases all the way until it reaches the 45 right at the end, just there. What are the radiuses that we have associated with this problem? We have R1 and R2. R1 is the thickness of the wire, and the thickness is 0.2 centimeters, so 0.2 radius, 0.2 centimeters radius, and that same thing is 2 to the minus 3 meters. And RR2 equals RR1 plus the thickness of the ceramic layer, which is, according to the problem there, 0.5 centimeters. So if that's the case, that's plus 0.5, which makes this 0.7 centimeters, or 7 times 10 to the minus 3 meters. Cool. Now, you'll see that there's an equation that when we're dealing with energy being generated, there's an equation we can use for these kind of cylinders. And for the cylinder with energy generation, the equation is Q equals, the difference in temperature, that is a temperature that we want minus a arbitrary temperature that we can measure, equals the energy being generated divided by, let's write it down. So T, any T that we want, minus a given T that is defined, has to be equal to the energy being generated, Ugen, okay, divided by 4K, which is related to the area of the cylinder, and the difference in radius, so R minus RO. Okay, so what is this saying? It's saying that first, to find a given temperature, we need another reference temperature. We need to know the conductivity of the material in question. And we need to know the temperature, the radius at the temperature that we want, and the radius at the given temperature that we know. So if we were going to translate this, we want to find 2 points right in the system here. We want to find this temperature right here. So T at the center. We also want to find this temperature right here. So T at the interface, Ti and Tc. Okay. The first thing it asks us to do is find the temperature at the center. So if I want to find the temperature at the center, what are my boundary conditions? Well, at the center, let's do it like that. At the center, my R equals 0, right? At the center, my radius is 0. And at the center, my temperature equals temperature at the center. So if I apply those boundary conditions here, what am I going to get is Tc minus To equals Qgen over 4K, sorry, RO squared. Okay, and it will be very tempting for us to think that we have the things that we need, because check out, that means that if I plug in 45 for my TO, right? So if I go in here and say that my next boundary condition is that at radius equals radius 2, temperature equals 45. If I were to apply that, it would be very tempting, right? Because that would mean that I would have this that I'm looking for, this that I'm looking for. I also have the conductivity of the wire. I have the Q generation, so I can find temperature at the center. But there's big problem doing that, actually 2 big problems. The first one is, note that the way this equation is set up, okay, there's no way for it to know, this equation for it to know that we have 2 different materials there. So there's no way for it to know that what is actually generating the heat, the Qgen, is only this inside part there and not the whole thing. So if I'm doing that boundary condition that I just put there, the green one, that would be incorrect because of that. The second thing is that there's only one case, or there's only one conductivity being accounted for. And if I'm doing that, I'm considering both the copper wire and the ceramic layer here. And I know they have 2 different Ks. And if you look at the equation here, there's only one K being considered. So if I do that, that would be incorrect. So I can't do that. I need to find a reference temperature for my copper so that I can solve this equation here. Okay, so I can't do this. I have to stop and find a reference temperature. So I have to find a temperature somewhere along the copper wire that I can use to solve that first equation that I came up with. But the other thing that I'm looking for is Ti. Remember? Ti, this guy here. Ti. And Ti is right on the interface. So I can use that Ti to my advantage, because if I can find this Ti here, I can use another boundary condition, which will be, let me write it here. At the interface, T equals Ti, and radius equals 0.2. Right? So as long as I can find my temperature for Ti, I can use it in this scenario here, because then I only have to worry about the copper. There's no ceramic layer anymore. Okay, so I'm off to find my Ti before I can find T center. And I did this whole loop knowing this would occur, just because it's a way that you would probably approach this problem. Okay, so now comes the hard part of the problem, because we need to find Ti. And to find Ti, we're going to have to do energy balance. Okay, so we're going to do energy balance. For us to do this energy balance, what I'm going to ask you guys to do is I want you guys to picture this ceramic layer. Okay, I want you to picture this ceramic layer in your heads. So I'm going to have you guys close your eyes and imagine this ceramic layer without anything around it or inside of it. So it's just a hollow cylindrical shell floating in space. And I want you guys to picture that in your heads, and that will be our control volume. So I'm going to do an energy balance in that control volume. All right. And Closing your eyes and picturing actually is going to help you guys a lot. Now, think about that ceramic layer floating in space, and we know that we have steady conditions going on. So we know that whatever energy is entering that floating ceramic layer, that hollow cylinder, whatever energy is going through that guy, coming from the inside and going through it, has to be leaving on the outside eventually, right? It's a steady state condition after all. So it's not like the cylinder is warming up as time elapses. It's just going to stay on that same temperature gradient throughout. So whatever energy is entering that cylinder hollow shell is leaving it eventually. Okay, so we can open our eyes now and you can look at what that would mean if we did a little energy balance, right? Energy balance says that we cannot create or destroy energy, right? So that means that whatever energy the ceramic layer has to be equal to the energy leaving the ceramic layer. Okay, and we know the energy that's entering the ceramic layer is due to the energy being produced by the copper wire. And we know that the energy leaving the ceramic layer is related to the conduction that this layer has. So the mode through which the ceramic layer is, quote unquote, getting rid of the energy is through its conductance, right? So what we can do is we can take this side of the equation here and say this is due to conduction, so this is going to be my Q. And I know my Q is delta T over R. I also know that my R for a ceramic layer like that will be natural log of R2 over R1, like we did before, divided by 2 pi KL. And this K obviously is for the ceramic layer, right? So I can combine these two equations. Actually, I can combine this R into there. So I can see that my Q will be 2 pi KL delta T divided by the natural log of R2 over R1. On this side here, I know this energy is coming from the copper wire. And I don't know that energy just yet, but what I do know is the unit on this guy, right? I know this guy is in watts per centimeter cube. So if I can find how many cubic centimeters this fella has, I can eliminate the need to do anything else. So I just need to multiply this Egen here by its volume. So to know the amount of energy the copper is giving out and that eventually going to go through the ceramic layer, all I need to do is get that E gen there, or Q gen, same thing, and multiply that by the volume of the wire. Okay, so 50 watts per centimeter cube. I can convert that if I want to. If I want to have everything in meters, that'll probably be nice. I can get rid of the C by doing times 10 to the 6th. And if you're confused by this, what I recommend is doing the method that I taught you guys a couple weeks ago, doing 1 by 1. And the volume of that copper wire will be the area of the wire, so 2 pi R1 squared times the length of that guy, which is L. Exactly the same L as the ceramic layer, okay? So I'm going to combine now the two equations, right? I'm going to combine the the green left side and the blue right side, because I know they have to be the same. So on one side here, I'm going to have 50 times 10 to the 6th times pi times R1, which is 2 times 10 to the minus 3 squared times L, which has to be equal to my blue side here, which is 2 pi. K for the ceramic layer, I forget what K for ceramic layer is, 1.2. L, delta T, that's the delta T that allows our energy to go from one side to the other. So we want the difference from the beginning of the ceramic layer to the end of the ceramic layer. So this is the delta T just here. And that will be my T interface minus 45, right? divided by the natural log, the natural log of the two radiuses. So the natural log of 0.7 divided by 0.2. And note here that the unit doesn't matter as long as they're the same, because they're going to be canceled out. Okay, so when we're solving this, 10 to the 6, 10 to the minus 3 squared, so that goes away. So I'm left with 4 on that side there. Pi goes away. The length of the guy, both sides goes away. So this turns out to be not as complicated as it looks originally. So that is telling me that T interface minus 45 is equal to 104. If you work units around, you'll see this will be Kelvin or Celsius, depending on the same thing, right? But since we have Celsius over here, I'll make sure this is Celsius over here too. That means that the temperature at the interface will be 149 degrees Celsius. Okay, so that is the temperature at the interface between the copper and the ceramic layer. One thing to keep in mind, very important, is that if you guys had reversed this, if you guys did 45 minus Ti, you would get something incorrect, okay? Doesn't work, okay? So if you wanted to do 45 minus Ti, you would have to have a negative here because your Q would be going on the opposite direction, right? So because we always try to work with our Q positive, and to do that, we always put the direction in which is going from the start, from the start like we did here, right? That means that we're always going to be doing the greater temperature minus the smaller temperature, right? Every single time. And because we know Q is going this direction, we know temperature here is greater than temperature here, which is greater than temperature here, which is greater than temperature here, which is greater than 45. Okay, so whatever Ti was, even though I didn't know what it was, I knew it was greater than 45. Okay, you guys happy so far? Or as happy as can be? Okay, got a couple of texts. So now we can finish off and find what's the temperature at the center of the wire, right? Because now we have Ti, and Ti is 149 Celsius. So I can go ahead and rewrite this equation here. Bottom there. So let's zoom in here. And the temperature at the center minus T at the interface will be equal to Q gen over 4K. R will be R1 squared. Okay, I just need to be sure that I'm using proper units here, or else there will be a mess. So check out what I'm going to do. 50 watts per centimeters cubed, right? You could convert this, that would be fine, no problem whatsoever. But you can be cheeky and do what I did, which is I'm going to convert K instead of converting Q gen. Because K, if you recall, let's check it out. Where's K? K, if you recall, I'm looking for K of the copper, right? We're looking for K of the copper, is this fella here. And that is in meters per Kelvin. And that's the same thing as 0.15 watts per centimeters per Kelvin, right? So I'm going to do exactly that. I'm going to put 0.15. That will be watts centimeter per Kelvin. Because that allows me to also have the R1 as 0.2 centimeters. This allows me to, these 2 centimeters gets rid of this centimeters cubed, and then this centimeter here on the bottom gets rid of this remaining one here. Okay, if you wanted to convert to times 10 to the 6th, obviously you could do that. It wouldn't change much. TC minus T interface, which is 149, equals, and that's going to be, we're left with Kelvin, by the way, right? Because goes down, and we're left with this Kelvin down here. Just goes to the top. Whatever that is, 3.33. And that could be Kelvin or Celsius, but since I have Celsius here already, I can't use Kelvin anymore, so I'm left with Celsius up there, meaning that my temperature at the center is 152.3. Okay, so we actually had to do the second part so we could find the first part, or else it wouldn't work for us. Any questions, doubts, discussions, controversies?